Now we saw example 4.3, and let me read the statement of example 4.3. There is another way of analyzing the uniformly polarized sphere as we have done in a previous example, this example 4.2, which nicely illustrate the idea of a bound charge. What we have really is two spheres of charge, a positive sphere and a negative sphere. Without polarization, the two are superimposed and cancel completely. But when the material is uniformly polarized, all the plus charge moves slightly upward in the z direction, and all the minus charge moves slightly downward. Figure 4.15 is in your book. The two spheres no longer overlap perfectly. At the top, there is a cape of leftover positive charge, and at the bottom, there is a cape of leftover minus charge, while at the center, they compensate each other, they neutralize each other. And it's a concept of basically a bound charge. What this example is telling you, that if you are having two spheres, and the spheres, one sphere is a positively charged sphere and the other sphere is a negatively charged sphere, and you just overlap them, then they will cancel out each other. Now when polarization will occur, they will not cancel each other out. Some surface bound charge will occur. So to illustrate this thing, if I move one of the sphere, let's say a bit down or a bit up, then what will happen, that if the one sphere which is negatively charged, for example, is moved a bit down with a distance d, then you see that some portion of it will remain not neutralized and it will have a negative leftward charge, while the other sphere from which it will slightly slide down, then it will have a positive leftover charge there, while at the center, wherever they will be overlapping each other, there will be no charge. It will be neutralized, so like there is no volume charge contribution and only the surface charge contribution. So basically this example is illustrating that case in a different manner, that how this thing will look like. And in problem 2.18 we have solved this thing, that electric field is equal to minus 1 over 4 pi epsilon naught q times d vector here over r cube. This is capital R in cube in order to dimensionally satisfy this thing r cube there. Now we can convert this one, like we know that QD is basically P here. P is equal to Q times D, and this P is equal to the polarization. We define polarization per this P over a volume, so it will be with a volume here. This is not potential but a volume here, so this comes out to be P 4 by 3 and pi r cube of the sphere. So for this QD, I can write this thing. So this is E equals minus 1 over 4 pi epsilon naught, and QD, so QD is P is this P into 4 over 3 pi r cube. And we see here that 4 pi is gone with 4 pi, and here we are having 1 r cube, so that r cube is gone with this r cube, and we are left with that E is equal to minus 1 minus 1 over 3 epsilon naught, 1 over 3 epsilon naught, and P, and we will mark it is a vector. Here mark it as a vector, because when pu mark as a vector, du mark as a vector. Here you will have to mark p as a vector then, and this is equal to minus 1 over 3 epsilon naught and p here, and in the direction of polarization it will go. So the direction of polarization is, we have seen here that it is opposite to the electric field, so we got the electric field there. Meanwhile, for the point outside, it is thou all the charge on each sphere were concentrated is at the respective center. We have then the a dipole with a potential, then it's a perfect dipole here, and the perfect dipole field will be the same as we have written here, 1 over 4 pi epsilon naught p dot r square. R means for r greater than r, you are outside of this sphere, then this is equal, v of r is equal to 1 over 4 pi epsilon naught, the field of a perfect dipole, p dot r over r squared, because it's just a dipole. Or when you go outside of this thing, then it's just a dipole and the field will be that of a dipole. Either you write it in this form or you do calculate then the gradient of this and you write the field is E of r equal to 1 over 4 pi epsilon naught and p sine of theta over r cube, and in theta unit vector. So you can write it like this, just applying the gradient in the spherical polar coordinates here, and this will give the field of this sphere. Means it is just to calculate this thing in a different manner, like generating the dipole or generating those surface bound charge, is the polarization charge here. So it's another way to do this thing.